Hey team, I'm Maddie. Welcome to Science Side Up. And today we're going to talk about wind turbines and some weird concerns that some folks have about wind turbines in terms of them stealing energy from the atmosphere and thus irreparably causing damage to the planet. Uh, Spoilers, that's silly. But we're going to take a look at it. We're going to do some math. I've got numbers written on this pad of paper. I did some calculations and we'll finish it up together here on stream. Yeah, so it's going to be so good. Yes, so continuing the pre-recording adventure, this seems to be going pretty well. Current pregnancy status is that all of my shirts are now crop tops because nothing I own will fit over my belly anymore. And I just try to spend all day, every day inside in the air conditioning, like laying on the floor under a fan, like my dogs do, right? Where they like spread their bellies out on the tile because it's cooler. But I can't spread my belly out on the tile where it's cooler because I can't lay on my stomach because there's a human there. Anywho, okay. That's what's going on there. And yeah, okay, so let's jump into stuff. So a friend of mine on Twitter, he is Age of Rocks, he showed me the following article. And this is from Medium and from honestly a pretty good science communicator. Okay, so here's the article. I'll make that a little bigger so you guys can maybe see it better. Okay, so it's on medium.com. There is a link to this in the description of this video. And like I said, Ethan Siegel is like, I don't read a lot of like pop science, but he's a pretty good science communicator. If we look at like his bio, he is an astrophysicist, a science communicator, and a NASA columnist, right? So he should kind of know what he's talking about. And this is honestly a pretty good article. I read through it. I would explain stuff differently as an atmospheric scientist, but that's okay. So the question that is the heart of this article is, could extracting wind energy change the weather? No. Again, that's the short answer there. But this is actually a question that was sent to him by a human person. So since wind turbines draw their energy from the wind, could they possibly affect the weather? Right. So he is just like, honestly, if he would just like made this article up, I was going to be very concerned. But since he's like specifically answering a question somebody has, no big deal. What I didn't want to see was like him creating questions and like creating pseudoscience when it doesn't need to be there. Yeah, so yeah, the short answer here is no. Extracting wind energy isn't going to change the weather. So let's talk about how I am just real confident in saying that out loud. And he does some math in here. I actually set up my math independent of him, so that's fun. And I'm going to use slightly different numbers than he does. I'm going to use kind of standard assumptions we use in atmospheric science, but since he's not an atmospheric scientist, he probably isn't going to be aware of that. So there's two questions here, right? And what we need to look at is the how much energy is in the atmosphere and how much do wind turbines take out, and let's say how much do wind turbines take out of the atmosphere if we were going to say power the entire United States by wind energy alone, right? That's kind of the question. And then yeah, that's the idea. So first of all, let's talk about what drives wind. Why do we have wind? That's a great question. Fundamentally, all motion in the atmosphere is driven by the fact that we are on a globe. There is a temperature difference between the equator and the poles. The equators the equator, there's not more than one of them. The equator is hot and the North and South Pole are cold. And nature doesn't like imbalance like that. It's going to attempt to make the temperature of the earth reach a nice equilibrium, right? And so that means moving heat energy from the equator towards the poles. And that fact is what fundamentally drives all atmospheric motion and all ocean motion. The motion, well, there's a song, right? Like the motion of the ocean and the blah, 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 blah. So fundamentally, at its most basic level, okay, I was trying to wear, I don't know why I'm still weird about like, I don't always like showing my shoulders. Blame growing up in like purity culture, but it's too hot. So I'm going to take off the second shirt I was wearing, except I'm sweating and so it's sticky. Okay. Anyhow, also, I'm sorry if you can hear my fan in the audio. I'm not doing this without a fan. The end. Okay. So, all the motion. Yes, okay, so that's what's going on. So, the thing that is driving wind and atmospheric motion in general is the sun. So we're not gonna like run out of wind, you know. We've effectively got an unlimited source of power there to drive winds. So we don't need to worry about that. But let's think about, this is a kind of a fun exercise and how to do a back of the napkin calculation. So let's just think about this. And so the math we're going to do is pretty simple. We're just going to find the kinetic energy of wind. So kinetic energy, right? We learned about that in like high school physics, most of us, maybe even earlier, maybe middle school. Kinetic energy is 1/2 mass times velocity squared, right? 1/2 mv squared. So that's not so bad. The only thing we're going to change about that is instead of taking mass, we'll just take density times volume. So we're going to take the density, like an average value of density at near the surface of the earth, and then we'll take the volume. So we're moving a volume of air across a wind turbine. I am going to estimate the turbine's like blades. Let's call that 10 meters. That's probably too small. Should we call it 100 meters? Because we're just going to do order of magnitude. Why don't we call it 100 meters just for fun? So yeah, let's do that. Okay. So that is this idea of the volume of air that we're moving across the wind turbine would be, yeah, like the height of the turbine and then times area. And the area here would be the entire surface area of the earth, right? That's the entire surface area of the earth. That's the energy we have to draw on. And what this is going to tell us is like at any instantaneous moment in time, how much kinetic energy are in the winds at about the height of a wind turbine across the whole earth. So how much of sort of think of it as like a power source we have to draw on. Okay, so that's what we're gonna calculate. So here's my favorite scientific web calculator. So 1/2 times density times volume times velocity squared. Okay, so the density of dry air is about 1 kilogram per meter cubed. Okay, so that's 1 kilogram per meter cubed times, let's do our depth times 100 meters, right? And then times the surface area. Oh, shoot, sorry, I can't put units when I'm typing into a calculator. That's not okay. Times the surface area of the earth, which I Googled previously, and I got that is 197 million square miles, which is about 5 times 10 to the 8th square kilometers, which is 5 times 10 to the 14th square meters. This is going to be times 5 times 10 raised to the 14th. Okay. Oh, and I did forget to put 1/2 out front. So this will be 0.5 times this. Okay. So 1/2 density. This whole thing is volume. And then we're going to take, okay, so a good order of magnitude estimate for wind speed near the Earth's surface is 10 meters per second. So if we're going to take a velocity squared, that's going to be 100 meters squared per second squared. So then this is times just 100. Okay, so cool. So we take this number and we get 2.5 times lots, right? So that is a kinetic energy of 2.5 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 times 10, 2.5 times 10 to the 18th. And our units here are joules. A joule is a Newton meter. A base unit of a Newton is kilograms meters per second squared. Kilograms meters squared per second squared. There we go. So we should get kilograms meters cubed per second squared for a joule. Okay, so great. We've got a number, which is awesome. So that's a whole lot of energy. And then, remember, this is the amount of energy that's available at any moment in time. So now let's think about how much energy does the United States use in a year? That was the easiest number for me to find. And I found that to be about 3.93 trillion. This is a unit here of kilowatt hours. So cool. Little refresher on units for everybody. 1 watt is 1 joule per second. So if we have something that's in watt seconds, that's the equivalent of a joule. So this kilowatt hours, that's a unit of energy, not a unit of power. Okay, so we need to convert our joules that we just found, the 2.5 times 10 to the 18th joules. We just need to convert that to kilowatt hours. Okay. So the first thing that would be easiest to do is let's take it to kilowatt seconds first. So I wish I had something to write on. One day I'll like buy an iPad and I can like write stuff on it while I'm sitting here chatting with y'all, because some of the stuff is easier to show. And again, I still can't get to my chalkboard right now because it has baby stuff in front of it. Yeah. Okay. Okay, so the first thing I'm going to do is convert my joules to kilowatt seconds, right? So the joules is an equivalent to a watt second, right? And so let's just make that. So 2.5 times 10 to the 18th watt seconds. Then let's make that kilowatt seconds. So there are 1,000 watts in a kilowatt, right? And so that means we need to divide this number by 1,000. So that's going to give us, so we'll divide that number by 1,000. So this is, please enter. Thank you. So this should be 2.5 times 10 to the 15th. This is now in kilowatt seconds. Okay, so 15th, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Brilliant. Okay, so now to convert kilowatt seconds to kilowatt hours. Um, so there are 60 seconds in a minute. So we'll take this times 60 seconds in a minute, and 60 minutes in an hour. So times another 60. Okay, so this gets us 9 times 10 to the 3, 6, 9, 12, 15, 18. Times 10 to the 18th. 9 times 10 to the 18th kilowatt hours. Great. 9 times 10 to that is 9 times 10 to the 18th kilowatt hours. Versus, okay, this 3.93 trillion, that is 3.93 times 10 to the 12th kilowatt hours. So at a second, a one moment in time, right? There is enough energy in the atmosphere across the depth ish of our wind turbines. Um, uh, there is 6 orders of magnitude more energy available than what, say, the United States needs. Okay, so that's 6 orders of magnitude. That is, let me use a money example. So that is if I have $1,000, the cost here would be a tenth of a penny. Right? So I have $1,000, and also remember that I get it, and I get a new $1,000 like every second. Let's just say every second. I get a new $1,000 every second, and I need 1/10 of a penny of one of those $1,000 to power the United States for a year. Right? So we're not taking a substantial amount of energy out. Okay. That's the short answer. That is the the short answer here. And that is eventually what our friend Ethan gets to in this article, which is great. I think he's a little rambly, I think, but that's just me. I think he explains more than you need to know to answer this question, but that's just me. So, like, I would have written this article differently, but of course I would have, because I'm a meteorologist. He's an astrophysicist by training. So, I, you know, I he'd probably have a lot of critiques about how I would talk about astrophysics, which is fair. Okay, but there are a couple points that are brought up late in this article that I want to chat about. Okay, and that is, okay. Cool. Um, no, see what I mean? He's like very. This is a lot of words. Okay. There are 2 effects that do play a substantial role, particularly over the short term. So there are going to be like 2 effects of wind turbines that can be important locally for short time periods. Okay. Okay. So the good one that he brings up is that wind turbines don't need water, whereas all other power, like nuclear power plants require water because they're going to be water. Generally, they're water cooled, used to produce steam. That steam is then used to drive turbines to produce power. A coal burning plant does effectively the same thing, except the heat source is coal, not nuclear fission. So a plus is that wind turbines don't need water for them, which is great if we're worried about water conservation, which we absolutely should be, especially as we're seeing droughts like the one in California becoming more common these days. Okay. The other thing I want to talk about though is this this concept that wind turbines locally increase temperature. Okay. Okay, the first is that wind currents, which naturally flow relatively rapidly over land masses, bringing the cooler ocean air with them as they do, would be depleted on large national scales. That's a huge oversimplification. One, um, uh, where I live, when we get ocean air, right, it's coming up from the Gulf. So that actually warms our state significantly. Because it's generally warm, moist air coming up from the Gulf of Mexico, compared to cold, dry air coming over the Rocky Mountains, right? So, um, that statement, cooler ocean air with them as they do, this is true like in coast on the coast, in coastal regions in particular. So this isn't universally true. Okay. Um and uh and I'm not quite sure these wind currents would be depleted on large national scales. He does cite a source later, but we'll talk about that source here in a second. So this is very much, I feel like there's a ton of caveats here that are not being addressed. Um, so what the wind turbines would effectively do, like it or not, is redistribute the heat throughout the atmosphere. That's also not really true. So wind turbines are going to exist in what's called the boundary layer. So, most people know, uh, that the atmosphere is like a cake or an onion or Shrek. It has layers, right? So we generally think of the troposphere, the stratosphere, the mesosphere, and the thermosphere. Those are the main four layers. You and I live and breathe down in the troposphere. Fun fact, like planes fly in the troposphere. All mountains exist in the troposphere. So all of our weather is happening in the troposphere. Okay. So if we're just going to look at the troposphere, then, excuse me, if we're just looking at the troposphere, we can also break it down into several layers. So the troposphere is like kilometers, it's very thick. It's taller than Mount Everest, Um uh yeah, sorry. I got really distracted. Um but if we're thinking about the boundary layer, which is the lowest level of the atmosphere, the subpart of the troposphere that touches the ground, um that's where turbines are going to live. So it's like the bottom 1 kilometer, right? At most 1 kilometer, maybe like 500 meters. Um, and as it turns out, um, so the math there is really really cool because that's where you get like small scale turbulence, and this is actually like meteorologists who study the boundary layer are the people who study the effects of turbines. Mostly what they're studying is like, where's the best place if I have one turbine here, hold on, I'll do this. Okay, I have one turbine here. Where should I put the next turbine so that it's getting the most energy? I don't just want to put it in the wake of my first one because then that's not maximizing my spatial distribution of turbines, right? Okay. That's a lot of what they're studying. And so, but the boundary layer is pretty darn stable. Uh, 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 so it has neat layers in it. And to mix between those layers, you need like turbulent mixing. And it's a very complicated thing. I actually kind of love the math of it. It's really cool and fun to think about. Turbulence in general is really fun to think about. Um, but the boundary layer represents like a distinct layer of the atmosphere, a distinct subset of the troposphere, and it kind of behaves a little differently. And um it's not super easy to move air from the boundary layer to what we would call the free atmosphere, right? That's kind of the main characteristic when we divide the atmosphere into these different layers, is that it's sort of hard to bust for the atmosphere to bust through different layers. Now it's easier to get through the boundary layer and into like the free troposphere than it is to get from the free troposphere into the stratosphere. That is easier to do. So it's a stronger boundary between the troposphere and the stratosphere. But remember, right, like hurricanes don't bust through the troposphere to the stratosphere. You need like a tornado, and even then, or a really, 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 really strong hail core, and even then, it punches up and then just kind of dies and stays there. So all of that to say, turbines would not redistribute heat throughout the atmosphere. It would add to the mixing of the boundary layer. So he's applying, and this is going to be because of a lack of understanding of the author here on boundary layer dynamics, right? So he's implying that this heat, the heat and the wind, that these turbines they're mixing the whole atmosphere, or they're mixing the whole troposphere. And I don't buy that, right? I would need to see a lot more rigorous study onto that than what is being presented here to convince me of it. And I would need to see, so prove to me that the effect of a wind turbine is more significant than the effect of the natural convection. So what happens with the boundary layer, in the mid latitudes, is that in the morning, you start to heat the earth, right? The sun heats the earth heats the atmosphere. And so you start to get these little convecting cells, right? And as the day goes on, the atmosphere gets warmer and warmer, right? And so as it's getting warmer and warmer, the strength of these convecting cells, and so how high they go, is getting bigger and bigger. So they're getting more and more energetic, more and more heat energy. And they are, so the height of the boundary layer, the height of the mixed layer, right? This is called the mixed layer. It's a part of the boundary layer. That gets higher and higher and higher. And then at night, that mixed layer kind of dies down as everything is cooling. We're no longer keeping this warmer air aloft, right? So it's all cooling down. Everything settles down. And then the next morning, it's like, all right, convecting cells, blah, 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 blah. So one, you need to convince me that a wind turbine is going to, the energy and the motion of the turbine blades is a bigger effect than those convecting cells in the boundary layer, for it to make a noticeable difference. And I mean, and that I could buy. That I could definitely buy. So it would make the creation of that mixed layer every day more efficient. But you'd be very hard pressed to convince me. But then you would really, really have to struggle to convince me to that this turbine, is going to redistribute this air all throughout the troposphere, right? That's not that. No. There's a lot of other things going on that would prevent that, in my humble opinion. I haven't worked the math on that, but I need to see it. Okay. Sorry, that was a long ramble, but I felt like that, that's a big thing that's being left out there. By altering the flow of the atmosphere, they'd exasperate the temperature differences between air over the ocean and air over land. Why? Okay, just because the land is going to be better mixed than air over the ocean. Okay. In theory, that would drive more winds. But okay. As was quantified in a 2018 study, large-scale wind power generation would warm the continental US by about a quarter of a degree Celsius or nearly half a degree Fahrenheit. Okay, so I looked up his source here, which is Science Daily, which is not the actual article. So what they did here was they used a weather model, and they covered a third of the continental US with wind turbines, and found that if you did that, um, uh, then you would warm the continental US by a quarter of a degree Celsius on average. And this was using, I think, a climate model. Um, okay. So I would love to see the actual paper. Oh, okay, here we go. Climate impacts. This is in Joule? Okay, hold on. Let's pull this up. Because I'm already sus of this study, I can think of a couple things. What is okay? What is this? What is this journal? Cookie settings, just strictly necessary, and we'll turn all the others off. Thank you. Okay. Okay. Okay, sorry, this is maybe gonna be boring, but I'm gonna jump down to the methodology. Oh, geez, they used a WRF model? Oh no. Okay, no. No. No, no, no. WRF isn't appropriate for this. WRF is a weather model. It's not a climate model. And I would need to know like uh uh yes, okay, wind turbine parameterization. There we go. Turbulent kinetic energy. We updated the wind turbine parameterization to make the wind turbine parameterization was originally briefed in WRF version 3.3, represents wind turbines both as a momentum sink and turbulent kinetic energy source. Cool. Okay. Okay. Okay, so by the way, this is saying okay, so this is actually very different. This is saying this isn't saying that they warmed like the continental US in a climate sense by a quarter of a degree, right? Because WRF isn't a climate model. It's a short-term weather model. So I think what they're saying is that they warmed it, like the turbines warmed that area by a quarter of a degree. That's over a short period of time. So that is like, is it? I think, right. I'm also not sure who these people are. But how good are their that TKE that so turbulence and the effects of these wind turbines are going to be happening at a sub grid scale resolution. And so you have to parameterize it. And I don't know if they're using the most appropriate parameterization. There's lots of stuff there. But I think what they're saying here is that raised the temperature by a quarter of a degree, not in a climate sense, right? Not an on average, but a like we went outside today and the high was supposed to be 70, but because of wind turbines, the high was 70.5. Right. That's what that's saying. As far as I can tell with that quick glance. Okay. And again, that's with a third of the continental US covered in wind turbines. So there's a lot of stuff in that I'm not really comfortable drawing. Oh, sorry. Oh no, you can't see what I just clicked to. Ha, that's not the window I'm sharing. So I'm a little like, I'm not sus of like that paper. I am sus of Ethan's reading of it, right? I'm sus of this article's interpretation of it. Because he is saying, uh, he is talking about that large scale wind power generation would warm the continental US by about a quarter of degree Celsius or nearly a half degree Fahrenheit. Um, uh, but would lead to a net temperature increase on annual or decadal timescales. So he is talking about climate timescale temperature changes. And I don't think that's what that article is talking about. Right. So it is true that locally, wind turbines might like raise the temperature right around them by I think by like a degree or so. So that is true. Um, but it's not like a global effect, if that makes sense. It's not universal, and um it's not increasing temperature in that climate sense. Okay. I hope that makes sense. Because again, the planet warming by an average of 1 degree Celsius does not mean that on average every day will be 1 degree Celsius warmer. That's not, those two statements are not equivalent. Um, not even a little bit. So okay, cool. I hope that makes sense. So I did want to bring up, so anyway, moral of the story is that wind turbines are good. They produce a lot of clean energy, and they're not going to mess with global atmospheric trends. I did want to show you some pseudo woo stuff that I found thanks to this Ethan's article here. And that is, I found this website, which is stopthesethings.com, the truth about the great wind power fraud. And here's a great picture of a turbine on fire. Weather makers, how industrial wind turbines are changing the world's climate. So, okay, as the mantra has it, wind turbines are the perfect panacea for rising temperatures. The ever fearful threat about the planet's temperature rising a couple of notches, apparently an increase of just 1.5 degrees Celsius, means instant disaster. Yes, this is actually quite true. Right, again, global average temperature 30,000 years ago during the last glacial maximum was about 4 degrees Celsius colder than it is right now. So it's very right. So an increase in temperature of 1.5 or 2 degrees Celsius is concerning, because that's, if we were to decrease by that much, right? We're halfway back to the ice age. Okay. And also it's very concerning, right, that we've gone up by 1.5 degrees Celsius in the last 100 years. And it took 30,000 for us to warm the previous 4, right? Those rates are very different. That's very concerning. Now, okay, so there's this, and then the people who hate wind turbines say, now it seems that these things are playing their part in adjusting temperatures, but not in the manner hoped for or predicted. Study after study shows local nighttime temperatures rising by as much as 1.5 degrees Celsius wherever these things are operating. So I'll just trust them that that's 1.5 degrees Celsius. Why not? This 1.5 Celsius and this 1.5 Celsius are not the same. This 1.5 Celsius is like, the whole planet on average warming, right? That's the like warming equivalent of halfway out of an ice age, right? This is near my wind turbine. It is 71.5 degrees Celsius. Far away, excuse me, sorry. It not 71.5 degrees Celsius would be insane. I mixed Fahrenheit and Celsius there for a second. Super sorry. 1.5 C. Let's just let's just call that 2 degrees Fahrenheit. So like this is like here it's 72 degrees Fahrenheit, but over here away from the turbine, it's 70 degrees Fahrenheit. That's what this number is. Okay. Um, okay. The climate cult is driven by a clearly burning desire to spear millions of these things into everyone else's backyards. Not theirs, of course. No, I'd be happy to have one in my backyard. I would love that. I would make so much money. Oh my goodness. So instead of keeping a lid on global temperatures, their drive to spread wind turbines far and wide have the precisely the opposite result. Again, no, he is confusing climate timescale change and climate scale change with a local, small scale weather effect. Two completely different things. Uh, cool. So that's fun. Um, Anyway, so there's a lot of fear mongering around this, apparently, against people who are very against wind turbines, which I think is very silly. I'll link this article down in the description below. Um, Anywho, let's see. Yeah, I think that's all I have to say on this. So the short answer, are wind turbines going to negatively impact climate? No, no. And I am now like redoubled in my assurance that most people don't understand the difference between climate and weather. And that's a little frustrating, but it's very important for me to know for how I talk about these things, right? Because that's a big thing of science communication. Even our friend Ethan, right? The astrophysicist and science communicator by profession apparently confuses the two. And so that's important to keep in mind. So remember, climate and weather are two completely different things. Um, and it matters if we're talking about climate or we're talking about weather, if we're talking about these like temperature changes. Um, Anywho, okay, team, that's all I've got for you guys today. I hope you liked this video. If you're not subscribed, I would love to have that subscribe. Otherwise, please leave a comment, especially if there's something like a question I can answer for you. Or, double check my math to make sure if I made a math mistake, let me know. Let me know down in the comments. And I'll be suitably embarrassed because I did math live on the internet and possibly made mistakes. Okay. If you are willing and able to financially support the channel, there's a couple ways to do that. Since this is pre-recorded, instead of a super chat, there's a thing called super thanks, which like tags your comment as special. And the other way would be there's a link to my buy me a coffee down in the description. Again, if you are willing and able. Otherwise, watch this with the ads. That's helpful too. And share it around. Let your friends and family know how cool I am in my chaotic life. But thank you guys so much for hanging out, and I will talk to you all soon. Okay, bye team.